As likely the last example for the basic probabilistic method, we will see an application of it in hashing. Okay, so let me set the context here. The universe that we consider has n elements. So without loss of generality, we will assume that the universe is the set which contains numbers 1 to n. And the number of buckets that we have, okay, we will see what this is going to be the codomain for the hash functions. These are the number of bins or buckets into which you can put in the hash values, or the number of distinct hash values possible is b, and most of the time it's again the set 1 to b. We will always assume that it's a set 1 to b. So your hash functions are all going to be from u to b. That's the idea. And we generally assume that this codomain is much smaller than the domain. Hence, an injective function is not possible, but we want something which is similar to the property of injection. That's the idea of hashing, right? So, what is that property that is similar to injection? We allow, we have to a priori pick a set of, or a collection of subsets of U. Okay, so some subset of the power set of U. Okay, so what is this C? C consists of not all subsets of U, but certain collection of subsets of U. And what we aim is that this function has to be injective on all these selected subsets. So if you restrict this function to any set in the chosen collection, then that function within that set has to behave injectively. That's the strong aim. Okay, that is when we say that this the function is a hash function for this family or this collection of subsets. But usually, I mean, when you take b very small, this is difficult to achieve. So instead of, we relax our requirement, and instead of looking for a single function which can do this, we talk about a collection of functions. Okay, or we talk about a small family of functions. And now, what is the relaxed requirement? If you pick any set, any set from your collection, then you should find at least one function in your family. Okay, so for any set in the collection, you should find at least one set in your family, such that the key requirement remains the same. F restricted to S is an injective function. Okay, so this is what we will work today, and these are referred to in literature by the name perfect hash families. Okay, so it's not a perfect hash function, but a perfect hash family, and the collection that you choose is most of the time going to be all subsets of a certain size. Okay, by the way, remember that there is monotonicity here. If a particular set S is in your family, then since F restricted to S is injective for at least one F in the family, F restricted to any subset of S is also injective. Okay, so there is whenever you take a collection and your family is a perfect hash family for that collection, it is also good if you include all the subsets of sets which are included in your collection. So most of the time when you speak about a family, you only kind of pick its maximal elements, maximal under inclusion. So the one starting example, which is mostly a toy example, is when C is the collection of all 2 element subsets of the universe. Okay, so the universe has 2 power n subsets, but we are only choosing n choose 2 of them, and not any n choose 2, but the 2 element subsets. This notation was already introduced in the last class. This is a family of subsets. It's the collection of all 2 element subsets of U. And let us say your number of buckets you have is 2. Instead of calling them bucket 1 and bucket 2, because for some reason I am calling it as bucket 0 and bucket 1. Okay, so can you construct a perfect hash family for this? Okay, so I want you to pause and think. The reason I want you to think about this question is that then you really understand what is the definition of a perfect hashing. Okay, so I think, I'm expecting that you would have figured out the answer yourself. What we want is, if you think about your family as some F1, F2, let us say some Fm, right? Then you can also think about this, vector valued function, right? You can think about a single function which works like this, which is a tuple of this f1 to fm, right? So what is f of x? F of x will be the tuple f1 of x, f2 of x, fm of x, right? Now, what does the requirement of a perfect hash family tell? It tells that for any two element subset, so pick any S to be any two element subset xy subset of your domain, then this requirement of perfect hashing tells you that at least in one of these functions, okay, so let me compute f1 of y up to fm of y, okay. The requirement tells you that at least one of these functions, they are different, okay. Now, so maybe at some ith position, this is some 0 and this is 1, or vice versa, f of x is 1 and f of x. So you at least need this position, okay. Now you notice that this f of x looks like a binary tuple, right, because your fi's, their domain is 0 and 1. So this is each component of your m length vector is going to be 0 or 1. So instead of writing it as an ordered tuple, you may also write it something like this, and you may write f of y like this, and what we are saying is that there exists at least one position in which the bits differ, okay. So this is the requirement, okay. So now this perfect hash family would have started to make sense. All that we are saying is that you find binary encodings of each of your member, each of the element in your domain, in your universe, so that for any two members in the binary encoding, they differ in at least one bit position, which is just a long drawn out way of saying that the binary encodings are different, okay. So you want injective binary encodings or one-to-one binary encodings of a set of n elements, right? Now you know how much that needs. You need for that to happen, it is enough if m is equal to the seal of the binary logarithm. We all know how to encode binary, right? So if you encode your, okay, let me assume that the universe is 0 to n minus 1, 0 will be encoded by 0, 0, 0, 0, 1 will be encoded by 0, 0, 1, and so on, and any two members differ in at least one bit position. And how do you now extract out your family of hash functions from that? Each bit position, this is your f1, this defines your f2, and so on, right? So your fi is 0 if the ith position fi of x is either 0 or 1. It is 0 if the ith bit in the binary encoding is 0, and this is otherwise, okay. Or I could have just written fi of x is nothing but the bit in the ith position of the binary encoding. So that's why I said this is a toy example. This is something which even those who have never heard about hashing would have come across. Okay. Now, just to I want you to understand this example before going to the next. Assuming you have done that, there's a small extension of this. Here, in the first example, we chose all possible two-element subsets of the universe as your the collection that you want to hash. But now, suppose you are only choosing a subcollection of the two-element subsets. Okay, so this is an easier problem than the first one. And how am I going to denote? How am I going to tell the programmer which are the sets that I want him to address? I am going to give it as a graph. Okay, so this would have been like giving the complete graph on n vertices. Okay, which means every pair has is a pair of interest. But here, if I only am interested in a subset of pairs, I can encode it by giving a graph of some sort to this, right? And now again, the buckets remain the same, 0 and 1. Now, can you find the perfect hash family for this of a small size? Okay, we are always interested in reducing the number of functions in your family. So we are looking for a small cardinality family which will do the job as small as possible. So yeah, it may be clear that you can do it with log n, because with log n you separate every pair, which means it will one function will be good for all the edges that are marked. But the question is, can you do better? In fact, in the particular example that I drew on this side, you can actually do with one function, right? You can, because all the edges, this looks like a bipartite graph. Okay, I mean it was accidental, but when I drew it, it turned out to be a bipartite graph. This is the first part and this is the second part. I actually need only one function. So you assign 0 to all the vertices here, and that function f will assign 0 to all the vertices here and 1 to all the vertices here. Now you see that every edge, since it gets 0 on one endpoint and 1 on the other endpoint, which means the function restricted to any pair which is indicated by an edge in this graph is injective. Okay, so if it is bipartite, you could do with just one function, but in general, what do you do? Like, let us say if it was tripartite, right, then if my bucket had 3 variables, I could have given 0, 1 and 2, and all the edges would be separated, because either their endpoints would be 0 or 1, which means it's injective on this 2 element set. Similarly here, it will be injective on this. But our bucket has only 2, but that's okay. What we can do is, you can use 2 functions. f1 would give, let's say, 0, 1, 1, and f2 should now distinguish this 1, 1. That's the key. This does not matter, maybe 1 and 0. So if you are taking an edge here, then that is injective in f1. If you are taking an edge here, this is also injective in f1. Yeah, what did I write? Okay, f1 is 0, 1, 1. This is f1. It is injective here, and if you take an edge here, then that is injective in f2 because of this, right? So again, 2 functions would suffice. Now I want you to pause and guess what would be the size of m. Okay, I'm assuming you have done that. We can do it with the binary log of the chromatic number of this graph. Okay, so what this tripartite, or if you have a graph which can be properly vertex colored using k colors, that means you can assign one of the k colors to each vertex of the graph so that no edge is monochromatic, but then no edge sees the same color on both its endpoint. But now you can also decompose the whole graph into k parts, such as each part does not contain an edge inside, it's an independent set. Then this trick will work. Okay, now first you label the color classes with 0, 1, 2 up to, let's say, chi many colors, and then you give a binary encoding for the colors. That's all that we are doing. Okay, I want you to verify that. In fact, in these cases, we can even prove that this is a necessity, right? So how do you prove that? For example, this in toy example 1, this log m is a necessity. You just reverse the argument that we were doing. So suppose f1, f2, fm was a good family, was a perfect hash family for this collection. Okay, now you assemble f1 to fm as a vector or as a binary string to follow m length binary vectors. Okay, so you had m functions, but together as a vector valued function, this gives a binary encoding for all the elements in the domain. Okay, and now the definition of hashing tells you that for any pair of functions, any pair of elements in the domain, you have one function at least where it is injective on the pair, which means in the binary encoding you have at least one bit position in which they differ. Okay, so you are looking for, so this problem is nothing but finding a binary encoding for n elements, and this I mean you can do now. I mean, I'm kind of assuming that this is already known to most of you as to the fact that to encode n elements in binary, you need at least log n bits, right? Your your 8-bit processors, the 256 is the maximum number of different things it can encode, and so on. You can work backwards, right? If you have only this standard product rule in combinatorics. If you have n bits, then you have exactly 2 raised to n distinct binary vectors of length n. So this proves that this is a lower bound. Okay. So a similar argument will work here also. Here also we are looking for binary encodings of the universe, but our requirement is weaker. We don't want every binary encodings to be different. We only want binary encodings of guys which have opposite, different colors to be, or only the endpoints of edges to be different. But then we should argue about a coloring in which the number of colors is as minimum as possible, and then you can visualize this binary vector that you treat here as a color. Okay, we were all comfortable treating colors as 1, 2, 3, 4 instead of calling them red, blue, green, etc., which means one more leap of faith and not faith, you'll see that instead of calling colors as 1, 2, 3, 4, you can even call them with binary vectors, right? Color 0, 0, 0, you have color 0, 0, 1, and so on. So you treat whatever this vector valued function gives you as a color. Okay, color is a bit vector, but bit vectors are also colors. If numbers can be colors, then bit vectors can also be colors. So these are colors. Think of this as a coloring that you give to the graph, and the property of hashing tells you that this coloring has to be a proper coloring, in the sense that if two vertices are connected by an edge, the endpoints, the colors should differ. Since binary vectors differing for two binary vectors to differ, all it means is that at least in one bit position they are different. Okay, so this gives a proper coloring. So so with some m number of bits, you have only 2 raised to m colors. So this 2 raised to m cannot be even smaller than chi fg, and this will tell you that this m is a tight bound. Okay, so this kind of a very tight bound we will only be able to achieve when your collection is as simple as pairs and so on. So when the collection that you are interested in, suppose that it is all the 3 element subsets. Okay, now this is a problem, right? A simple binary encoding may not work. Okay, so your 0, for example, let me take the easy case, 0, 1, and 2. What would be their binary encoding? Say it was 3 length. Okay, so 0 and 1 differ in the first position. 0 and 2 also, they differ in the second position, right? This and this, and first and second, 1 and 2 differ in the second position. But still, there is no single function. Okay, so this is your f1, this is your f2, this is your f3. But still, there is no single function which is injective on the set 0, 1, 2. Okay, so you have one function which is which separates pairs for any pair, but if you take 3 at a time, then you take f1, everything is assigned to 0. f2, it is still not injective because 0 and 1 are mapped to the same bucket value. If you take f3, 0 and 2 are mapped to the same bucket value. Okay, so a simple binary encoding will not work. Even if you had 3 buckets, a ternary encoding also need not work. You can think about that. So here the problem becomes slightly more complicated. Yeah, by the way, before going into the formal definition of the parameter we are studying, if you are interested, you should pause now and try to apply probabilistic method and find out how you can come up with again something which is a order of log n sized family for this also. Okay, there may be a larger constant than 1, but you can still find an order of log n. And if you have understood the spirit of the probabilistic method, there is only one direction to go, right? If you don't know to construct an object, construct it randomly and show that the probability that it is a hash function, it's a hash family, is greater than 0, from which you can conclude that there exists a hash family of that size. Okay, now which is the size? You start off the proof by putting that as a variable, and then after you have completed the calculation, do some more jugglery to see what value of m is enough. Okay, but instead of doing it for you choose 3, I will do it for you choose k. Okay, so these are known as this number h n b k, right? This is the smallest size of a perfect. So yeah, the smallest size is what we are interested in, which would have been obvious. Smallest size of a perfect hash family for the collection universe choose k. Okay, so we have seen universe choose 2 in detail. I hope you have all worked out universe choose 3 by yourself. We'll do this for universe choose k with b buckets. Okay, so what is the requirement? We want to find a family of functions F1 all the way up to Fm with m as small as possible, such that if you pick any set, okay, which is of size k, so any set S which is a subset of 1 to n and size is equal to k. So these are the members of this collection. You should be able to find one Fi in your family F such that this Fi restricted to S is injective, okay, which means all the k elements here are assigned to k different values. Okay, by the way, I think now that I see, oh my god, I should have probably confused you all a lot, right? It should have been at least 3, right? Because how do you get an injectivity on 3 sets if your buckets only had 2 elements? Okay, so yeah, that was a mistake. And I hope you would have realized that this was not possible. So now I want you to pause again and go back and see with b either 0, 1, 2 or larger, will you be able to do this? Okay, so here I should actually insist that this b has to be at least as large as k. Okay, the number of buckets has to be at least as large as the largest set in the collection that you want to separate. Okay, and otherwise there is no scope to get this injectivity. Okay, and our theorem would be to prove an upper bound of HNBK. We kind of know that the dependence on n is going to be logarithmic. There would be some log factor of n coming in. But we are also interested in seeing how b and k will feature out in the bound. Okay, so our aim is to show, let's do our typical random experiment steps. 1, construct f is equal to some f1 to fm. This value of m we will fix at the end of the proof. Fm independently and uniformly at random. So what does this mean? So how do you construct one function? Let's say, how do you construct f1? You know that you have to, in the domain which is now n, you have to map each point to this buckets, right? 1, 2 up to b. This is your bucket set b. So this has b choices. It can be mapped to any guy. This has b choices and so on. So you have b power n choices for Fi. So you can pick one among the b power n choices uniformly at random, which if you want to decompose this experiment further, it is like tossing a b-sided coin at every vertex in your domain or at every point in your domain and assigning it to the value that is shown by the coin. Okay, so if you have a b-sided coin or a die, you throw that at each vertex, and that way you can decompose this, and then you do that independently for each of the nodes. Okay, but this is, yeah, so this will also give you each possible function among the b power n choices equally likely, right? And now when you go for f2, repeat this whole experiment independently of what you have done before. So that's the first step. Okay. Second step is to do the main probability calculation. So what is the probability that you have to calculate? You have to calculate the probability that this f is a perfect hash family, or since we are going to use a union bound, because you see that the definition of this hashing is also at least one function is good for any given subset. Yeah, so you will again use a union bound here. So we will be most likely showing the probability that f is not a perfect hash family. PHF is for perfect hash family. We will have to calculate this probability and then show that for large enough m, we will have to show that this probability, let me call it as q, we have to show that q is less than 1, and then your philosophy. Okay, because if the probability of not finding a perfect hash family is less than 1. This can only happen if there is at least one family in your sample space which is good. Okay, so the first part is already done. I described what is the experiment. Now again, I want you to pause because it's the last problem we are going to do using the basic method. Here I want all of you to pause and do it yourself and only come back to the video to check your answer. Okay. So assuming you have done that, let us do the details of step 2. Okay. Again, let me try to do this computation in one shot because I'm expecting you are here only to verify it. Okay. So what is the probability that for a given set S in the domain, so S is a subset of this n choose k, right? S is a member of this one of the k element subsets. For a given set S which has k elements, what is the probability that a given function f in your family separates it? So that is among how many injective functions are there divided by how many total number of functions from S to this bucket set B, right? So the total number of that is because, or you can say that at each point each point inside of S. Okay, so S is sitting somewhere here. At each point of S you have B choices for each of the k members in S. So these are the possibilities there, out of which in order to get injectivity, the first guy had all the B choices, the second guy only had B minus 1 choices, and so on, B minus k plus 1, right? So this is the probability. This numerator I will denote it by, okay, this I will denote it like this. So this is in some sense not a very rare notation, this bk with an underscore. If you see an underscore in the exponent, what it means that this is a falling factorial. So the first term would be b, the second term would be b minus 1, and you take k such terms. Similarly, there is also a notation like bk upper bar, which would be b into b plus 1 into b plus k minus 1. Okay, so this we won't use here, but this is called the falling factorial or falling power. Yeah, falling exponent. Okay, so this is the probability that S is injective. Okay, and this is going to be a low number. So the probability that S is injective, F is injective on a given F is injective on a given S is this number. Now the probability that it is not, a given F is not injective is this. Now the probability that for this given S, none of the m f's in the family, this f1 to fm, they are injective is this to the power m. Remember that there is an independence here because the f1, whatever the choice of f1 is independent of f2. All these m choices are mutually independent. So the probability, the probability of a particular set being bad, no function in your collection being injective on S can be written as this power. Okay, so this now calculates, this now covers all the functions in your family, but now you have to worry whether at least one S in the collection is bad, right? Remember, what is Q? Q is the probability that it is not a perfect hash family. For something to be a perfect hash family, it has to separate every one of the n choose k possible sets. But the probability that at least one of them is bad is not equal to this, but it is less than or equal to this because of the union bound. Okay, so this is the Q that we are going to calculate. Okay, so I hope you also got the same answer when you did the calculation. Now, what is our next aim? Our next aim is to show how large an m do we need so that this number here is less than 1. Okay, so again we work this implication backwards so that we can put upper bounds here. So I am trying to be a bit conservative here, unless I need a k fact, this e, I mean I could have substituted, as we know this is e n over k to the whole power k, but I think this is enough. Okay, maybe yeah, this is enough, and this is 1 plus x upper bounded by e power x. Both of the bounds we saw in the last class, so I'm not repeating how we got them. I mean, I did not even prove how this comes up, but you can refer Wikipedia also. So this is e raised to minus bk falling factorial by bk. It is enough to show that this is less than 1, which means if you take logarithms k ln n minus b. No, where did I lose the m? Okay, there was an m here, so you have an m here. M less than 0 is what we know. Again, good thing is that m is sitting alone. In some cases, your m will also get inside the other terms and it will clutter. So this again, since this is a strict bound, this is strict unless x is equal to 0, right? Which is not going to happen in the cases of interest. So here it is enough to have this. Okay. So this means it is enough. By the way, this is not significant. You might only lose a value of an additional +1 if I use this strict inequality instead of less. Okay. So don't get confused about whether to use the strict or the unstrict inequality. Okay. So what does this tell? Okay, maybe I'll write it in 2 more steps. Greater than k ln n, or right. So this is the, if your m is at least this much, then q is, so that's what we are saying, right? What we are saying is that if m is at least, no, I missed a k somewhere. Yeah, there is a k here. Okay. Yeah, so if it is at least this, then q is less than 1, which means, and hence their x is so your m has to be an integer, so this would be something like this, right? Seal. Then their x is a perfect hash family of m b array functions for this n choose k. So now remember what was your h of n b k? Okay, this was the smallest size of such a family. We have proved that for this m there is such a family, so the smallest can only be smaller or equal to this. Okay, so this number that we have proved is an upper bound. Okay, so as expected, we got a logarithmic dependence on n, and yeah, we got a logarithmic dependence on n. We got a linear dependence on k in one sense, but again, k is also kind of sitting here. So yeah, the dependence on a k is a bit more complicated. Okay, but yeah, now I'm ready to. Oh, I don't have space to put the value here, so but let me still see. Okay, so we have shown that this is less. This is our theorem. Okay, yeah. So the dependence on k is a bit more interesting. This falling factorial, if you just approximate it by, like if when b is much larger than k, when your number of buckets possibility, number of buckets is much larger than the size of the sets in the family, then this is almost 1. Okay, because this falling product will not really reduce the value. Then this is mostly like k log n. The bucket size will not matter. But if the bucket size is very small, in the examples the toy examples that we saw, our bucket size was approximately equal to k, right? And we know that the smallest bucket size that is affordable is b equal to k. So yeah, if B is much less than K, then this is approximately KLNN. But if the bucket size is equal to K, then this is like K power K by K factorial times K ln, and then you know that this K factorial is more like K to the power more like K factorial is more like K by E to the power K. So this K to the power K and K to the power K will go, and this whole thing here will almost look something like E to the power K ln. So yeah, so when K is, when the bucket size is close to K, the dependency on K is almost becoming exponential in K. Okay, now this is the this is the upper bound. So is there any lower bound that we can write here? Yeah, we already know we said that in order to split, if you split every k-sized set, if you have an injectivity for k-sized sets, then that means there is automatically an injectivity for two-sized subsets or any subset of that, right? So any perfect hash family which is good for k-sized sets is also good for two-sized sets, and for two-sized sets we already know of a lower bound in terms of log n, which it was binary encoding. But now you can say if it was a b-ary encoding, then you can do it with log b n bits, right? So because in each place you have b. So this is one lower bound, which is the problem is that it is kind of completely ignoring k. But there is a way to bring in the dependence on k also here. And the best known answer is something like, I think you can put b to the power k minus 2 by b to the power k minus 2 falling factorial here. So there is a gap of around b squared, approximately b squared between the lower and upper bounds. Okay, so we won't prove it right away. In fact, for the hash family, perfect hash families that we saw in the last class also, yeah, we really did not prove this k minus 1 factorial. So maybe we'll actually take one class. I'm kind of hesitating to do the lower bound because the lower bound is not a probabilistic argument, but it is also, in order to be more familiar with this problem, it is good to see how lower bounds are done for this. Moreover, both of these lower bounds are involved. Each one involves one very nice trick. Okay, so how to it's almost like stepping up one lower bound that we know for like the two case into the higher cases. Okay, so maybe we will see that in the one of the next classes, but for now we will wind up with this. So I hope with this you are all comfortable with the basic method. We will move on to the second method, which is called linearity of expectation, or the first moment method, from the next class. Okay, so remember, this pattern is what you should always know if you are going to construct a combinatorial object, but you are kind of stuck as to what is the best way to construct it. Then instead of thinking about the best way, try to devise a random experiment that will construct this, generate a family containing these objects as uniformly and as independently as possible. This uniformity and independence is not a philosophical requirement. It makes the second step easy, because when you do a probability calculation, uniformity will help you where, in the union bound, instead of adding things up, all the constituents of the addition are of the same value. So you can just multiply it with the number of elements in the summation. So uniformity helps there. Independence helps in getting powers and so on. So choosing them independently and uniformly at random is so as to make the step 2 very easy, the calculation very easy, right? So here the experiment is unlike in a usual probability course where you are given a random experiment and you are analyzing its probability. Here the main challenge is to design the random experiment. And when you are designing the random experiment, you will design it in a way so that your analysis becomes easy, and your analysis is something that will take some time. After, again, you can only you'll need some practice to get going, and then you show, most of the time your object will have some parameter, the parameter of interest, and this probability calculation will throw up a formula which involves that number. Now you tweak that number in order to get the probability. If it's a bad probability, you want it to be less than 1. If it's a good probability, you want it to be greater than 0. You find out the optimal m for which this is guaranteed, and then the probabilistic method, probabilistic method standard argument will tell you that this is complete. Okay. So yeah, thank you.